Okay, hello and welcome back. This video will cover 2.6 more applications of linear equations. This time we're going to use proportions and solve equations with proportions. There's some money problems, and the last example we'll see is a question involving distances and rates and time. All of these will involve proportions in some way. So let's get started. So the first section is on using ratios. And they define a ratio as a quotient of two quantities. Oftentimes you'll see, you can view a fraction as a ratio, something divided by the other thing. Um, and there's two ways we can write it. One is as a fraction, so they say the ratio of the number x to the number y, where y is not equal to 0, so that's just the side condition, can be written as a fraction, x over y. This is why y can't be equal to 0 because we would be dividing by 0 there. You could write it out verbally as x to y, like what's the ratio of something to something. Or you might see it like this, x and then with the colon y ratio. Sometimes you see like betting odds in that kind of format. Okay, so let's look at the first example. It's asking us to write the ratio of 4 feet to 2 yards. So we can imagine 4 feet on top of a fraction to 2 yards. And what we want with these is to get the same units. Notice the top is in feet and the bottom is in yards. So we will have to convert one of those to the other so that we can actually get a proportion. At the end, we want something without units in a way, like we want them to cancel. So let's use the fact that there are 3 feet and 1 yard. So um, you may need, don't be afraid to search for some of these conversion factors. They might throw some units at you that you're more or less familiar with. So you may need to find out how much, like how to convert between them. So knowing that there's 3 feet and 1 yard, let's turn yards into feet. We have 2 yards, and I'm going to multiply by this conversion factor. There's 3 feet and 1 yard. And this is kind of a simple example, but you do this kind of work if you're doing dimensional analysis, like in chemistry class, you might have to convert between units a lot, and it comes up in other contexts as well. So, excuse me, in general, you want to set up a multiplication, and I'm saying there's 3 feet in 1 yard. So the trick is to put the unit that you want to convert to on top. Like I want to convert to feet, so I'm going to say 3 feet on top here. And then the unit that you want to cancel on the bottom. There's 3 feet to every 1 yard. So notice here, and we can see the 2 yards as like 2 over 1. The yards here will cancel, and that's what we want. We want to get rid of the yards and end up with feet. So notice here we're just multiplying 2 times 3, because there's 3 feet for every yard and we have 2 yards, so the result will be 6 feet. Again, that's a pretty simple example, but we'll use that same strategy of setting up a multiplication by a fraction where the units we want to cancel are on the bottom and the units we want to convert to are on the top. So make that look more like an F. So let's go back to our original proportion we had. We were saying 4 feet to 2 yards. But we just said that 2 yards is 6 feet, so let's replace the 2 yards with 6 feet. So we have 4 feet to now 6 feet. So in that case, the units cancel. Oops. Let's do this. So really we have 4 over 6. And then let's reduce this fraction. Remember, to reduce a fraction, we want to try to divide the top and bottom by the same number in order to make everything smaller. So these are both even numbers, so I can divide them both at least by 2 and see what we get. So 4 divided by 2 is 2. 6 divided by 2 is 3. And this is as reduced as we will be able to get to. So our ratio can be expressed as 2/3. 4 feet to 2 yards is a 2/3 ratio. Let's look at another application type problem. This is about trying to find the best deal given different sizes. Because a lot of products will be sold in many different sizes, and it's hard to tell which one actually gives you the best deal. So in this case, we're looking at ice cream. Sold in 3 different sizes. So they have a 4-ounce size, a 14-ounce size, and a 28-ounce size, and they each have their associated price. So $1 for the 4-ounce, $3.49 for the 14-ounce, and $7.39 for the 28-ounce. So the question is, which size is the best buy? Meaning, which one is the best deal? Another way to say that is which one has the best price per ounce, per unit. So let's find that out. That can be the first question that we ask. What is the price per ounce for each size? So what we want is, since we're saying price per ounce, the price is in dollars. So we want some kind of ratio where we have the price in dollars on top and the number of ounces on the bottom. That will give us our costs per ounce. So let's go through for each of these and see what we get. For the first size, it's $1 for 4 ounces. So let's take the price, which is $1, and divide it by, so $1 divided by 4 ounces. So 1 divided by 4, you'll get a decimal, 0.25, which is 1/4. Imagine a fourth of a dollar, which is a quarter, or 25 cents. So we can say $0.25 per ounce. That's how much you pay for every ounce in that size. Let's do the same thing for the second size. In this case, it's $3.49. And it is a 14-ounce size. So if you do the 3.49 divided by 14, you should get 0.249. And let me just double check and see if there's some rounding there. So 349 divided by 14. Yes, definitely some rounding. So we're rounding to the third decimal place here, 0.249. So notice this is a little bit cheaper per ounce, slightly. And then let's look at the third size. This one has you pay $7.39, and the size is 28 ounces. So 7.39 divided by 28, and let's round to the third decimal place. it will be 0.264. $0.264 per ounce. So like 26 cents and plus a little more. So the best deal will be the smallest cost per ounce. And these are all pretty close, but this could be a big deal if you're buying large quantities maybe. So it looks like this, 0.249 per ounce. This will be the best price. So we were setting up a proportion of the price to how many ounces. We're able to see the ultimate cost per ounce. So we would say the 14 ounce is the best price. So this is a good way to see, because they can be a little bit tricky with sizes and packaging and things like that. I don't know if it's true at every grocery store, but I know at least at H-E-B, if you look at the ticket or the price for an item, usually they give the whole price. Maybe it's like, so let's say we're looking at the 14 ounce size, and the price for the item is $3.49. They have a little price, and I don't know if they're required to do this by law or anything. There's a little price on the corner that will be the price per ounce, 0.249. And it may not be ounces, but maybe some unit of measure. And it's a really quick way to see which one is the better deal. You'll probably have like multiple products next to each other from different brands, and they might be slightly different sizes. And oh, um, one looks more expensive, but you're actually getting a better cost per unit. Like you're paying less for the volume. So just a little tip there. You can look for this cost per unit of measure as a way of comparing items at the grocery store. And you could apply this to other examples too. All right, let's look at some more like small equation style setups. So I've been using this term proportions. Um, so in the wider sense, if a proportion is a statement that two ratios are equal. So if you see down here, we can see two separate ratios equal to each other. Maybe I should have been using the word ratio earlier as opposed to proportion. And this property that they're describing, calling it cross products, saying if A over B, that would be 1 ratio, is equal to C over D, then A times D equals B times C. All this is saying is you can multiply both of the denominators over to the other side. And that's a common strategy for solving these kinds of questions. So we'll see some with a variable in example 4, but example 3 is asking us to determine whether each proportion is true or false. It's hard to tell just by looking at it. Is 5 over 7 the same thing as 15 over 21? We could just try to reduce this second fraction to see if we get 5 over 7. That's another sort of framing of this. It's asking if we reduce this fraction, do we get 5 over 7? But you can use this cross product idea in order to see if you get something equal to the same thing, something equal to itself. And I'll show you what I mean. So for A, we're starting with 5 over 7, and this is equal to 15 over 21. So I'm just going to take the denominator from each side and multiply it over, just like if we were solving an equation. Since this is a division, the opposite operation is multiplication. And then the 21, I'll multiply over as well. So we can view this as 5 times 21 equal to, or we're asking, is this equal to 15 times 7? So if you multiply these out, 5 times 21 is 105, and 15 times 7 is also 105. So since they're the same number, we can say this is a true proportion. Let's look at the second one, and we'll do the same thing. So this one says, is 2 over 9, is this equal to 7 over 36? So let's multiply each denominator over. So this would be saying, is 2 times 36, is that equal to 7 times 9? 36 times 2 is 72. 7 times 9 is 63. So these are not equal to each other. Therefore, we would say this is false. We won't be doing this kind of thing too often, but I would assume there's probably a couple homework questions that ask something of this nature. So a way to tell if two proportions are equal, besides just trying to reduce one of them into the other, is to do this cross multiplication and see if you get the same thing on both sides. So let's see an actual equation. This is a bit more like what we'll see. And we might have seen something like this before when we were in our solving equations section. So I have 16 over 24 is equal to x over 3. And it's wanting us to solve, which means we want to just get x on its own equal to everything else. So we could do a full cross multiplication, but notice if we just multiply this denominator on the right side over to the other side, we'll solve it for x. So in this case, I'm just going to multiply that 3 over. But we could still do it. We would just end up dividing by that 24 in order to get it back over to the other side. So we just undo our work. So when it multiplies, it'll multiply up into the numerator. So this will be 16 times 3 over 24 equal to x. And then we can try to be a little tricky here. We could go ahead and multiply 16 times 3. But we can try to reduce before we multiply things out. It might make reducing the end fraction a little bit easier if I note that 3 goes into 24 8 times. So I can imagine dividing the 3 by 3, and that will reduce to 1. And dividing the 24 by 3, and that will reduce to 8. So this whole thing would just be, on the top I have 16 times 1, so that'll be 16. And then 8 on the bottom. So 16 divided by 8, and this is still equal to x. I know 8 goes into 16 2 times, so this should just reduce to 2. You could have just multiplied that out in the numerator, the 16 times 3, and then divide it by 24. That would get you there too. Let's look at B. So we have k plus 2 divided by 2 is equal to k minus 4 divided by 5. And we want to solve for k. So this one's a little more complex. We want to get rid of these divisions, get rid of the fractions, and get all of our k's collected until at the end we can just say k equals some number. So here I'll cross multiply on both sides. Because once we have everything flat, there's no fractions like this, we'll be able to solve like from one of our previous sections. It'll just be an equation with variables on both sides. So I can view this as 5 times k plus 2, because 5 is going to multiply by everything on top. And then similarly on the right side, we'll have 2 times k minus 4. So yeah, now we have an equation like we've seen in some previous sections. So let's go ahead and solve for k. We'll first want to get rid of the parentheses by distributing both the 5 and the 2 through. So this would be 5k, 5 times 2 is 10. And then on the right side, 2k, and then 2 times negative 4 is negative 8. Now I want to get all of my k's together, so I think I'll subtract this 2k over to the other side. So 5k minus 2k is 3k. Still have the plus 10, and then we still have the minus 8 on the other side. Now let's subtract the 10. So I'll get 3k. Negative 8 minus 10 will be negative 18. When I subtract from a negative, it becomes more negative. And then we have 3 times k, so let's divide. I'll divide by 3 on both sides. So we'll cancel here. And then on the right side, 18 divided by 3, and it's negative, that'll give me a negative 6. So k equals negative 6. So in general for these, you can just multiply, cross-multiply each side. If you already have something like this, you might want to just multiply that 3 over like we did. Or if it's something more complicated, just cross-multiply and then simplify and solve like we've done previously. All right, let's look at example 5. So we have a word problem. So let's read through and try to get the information that we need. So it says Kaylin is an artist and she wants to make turquoise paint by mixing green and blue paints that she already has. To make turquoise, she will have to mix 4 parts of green with 3 parts of blue. So that's a ratio. And then we know that she's using 6 ounces of green paint, and we want to find out how much blue paint she should use. So let's set up a ratio. We can say what we want is a 4-part green, so we can imagine 4 parts 4 parts green to 3 parts blue. So this should be equal to what we have. We know we have 6 ounces of green. And we want to know how much blue paint we should add in order to achieve this ratio. So we can say 6 ounces of green to, oops, some unknown, let's say X ounces of blue paint. So we have a little equation. We can kind of drop the green and blue and just look at this as 4 over 3 should equal 6 over X. We'll know that X means the ounces of blue paint that we have. So let's just cross multiply. Let's multiply this X up into the numerator over here. And then we'll multiply the 3 by the 6 in the other numerator. So this should be 4 times X equals 6 times 3. And let's jump over here. 4 times x is just 4x. 6 times 3 is 18. So we have 4x equals 18. So let's solve by dividing both sides by 4 to get x on its own. So x equals 18 over 4. Let's try to reduce this. I know I can divide by 2 at least. So let's divide the 18 by 2 and divide the 4 by 2. 18 divided by 2 is 9. 4 divided by 2 is 2. So 9 over 2, we can't divide it anymore, so let's just turn this into a fraction. If you do 9 divided by 2, or turn it into a decimal, I mean, you'll get 4.5. Half of 9 is 4.5. And we had ounces of paint here. So we can say you will need 4.5 ounces of blue paint. So you can apply this to a lot of like recipe style questions where there's some known proportion and then you have some value that you do know and some unknown value and you want the proportions to be equal. That's what we did here. And this can be a really useful technique for solving problems in like a few different classes. Like I can remember doing this in like chemistry, maybe some biology type questions. You can solve using this proportionality type of method. So it becomes very useful. Cool. So in example 6, we have a situation involving two triangles, and we're going to use a property of what's called similar triangles. When they say that these two triangles are similar, what they mean is that one of them is just like a scaled up version of the other one. It's like if you took this one and zoomed in, or just made it larger, you get the second triangle. Another way to say this is, notice that these two angles are the same. They have the same symbol. These two angles are the same, and these two angles are the same. So they have all of the same angles. It's just the side lengths have been scaled by some proportion. So when you're told that triangles are similar and you're given some unknown side, you can use this fact that they are proportional. And let me just write it out. So this is a key thing if you see this idea of similar triangles. So similar triangles have proportional corresponding side lengths. So I'll show you what I mean by that. We're trying to solve for x here. So since everything has just been scaled by some factor, I can say the ratio of this unknown side length to the one that corresponds to it on the other triangle, meaning the one that's in the same position. So I can say x over 30 should be equal to the ratio of two other corresponding side lengths. So let's take, for instance, this 12 and this 18. These are both in the same position. So these corresponding side lengths should be proportional. So x over 30 should equal 12 over 18 because they've both been scaled by some factor, by the same factor. So let's just solve for x. This is a case where I'm just going to take this 30 and multiply it over because I'm just trying to get this x on its own. I don't want to add anything to it. I don't want to multiply the 18 and have to remove the 18 later. So I'm saying x equals I can write this as 12 times 30 over 18. You could just type this in, try to get it, but let's say we weren't using a calculator. Well, I know 6 goes into 12 and 18. 6 goes into 12 two times, and it goes into 18 three times. So you can imagine dividing the 12 by 6 and I get 2, and the 18 by 6 and I get 3. So this would reduce to 2 times 30 over 3. And I know 3 goes into 30 10 times. 3 times 10 is 30. So I can imagine dividing the 3 by 3 and getting 1, and the 30 by 3 and getting 10. We can reduce that way. And then notice here, this is just 2 times 10 up top. So that should just all be equal to 20. So overall, I can say the missing side length should be 20. I don't think we have units here. So if you have a similar triangles problem, set up some proportion between corresponding side lengths. We said the ratio of this unknown to this known on the same side should be the same as the ratio of these two knowns to each other. All right, let's go to the next section. So these are some kind of strange questions involving money, and really it's still about converting units, coming up with some kind of unit conversion. So let's look at example 7. It says determine the amount of money you would have in cents and in dollars, so two different units of measurement for each of these situations. So let's look at the first one. The first one says we have 9 nickels. And we want to convert that to cents and dollars. So let's start with cents. And we're going to do that unit conversion where we multiply by some fraction. And I know I want to cancel the nickels, and I want to pick up cents as my unit. So how many cents are in a nickel? Well, I know that 5 cents make up 1 nickel. So this is what I would want to multiply by. So the nickels will cancel, and then we'll get cents as our result. So really, I just want to do 9 times 5. We have 45 cents. And then the next part is asking in dollars. And I mean, I know I would just put this as 0.45 to express it in terms of dollars, but let's keep practicing this unit conversion. So I have 9 nickels. And then let's say I want to cancel the nickels and turn it into dollars. So how many nickels are in a dollar? Well, there should be 20 because they're each worth 5 cents. So 5 times 20 is 100. That would make it $1. So in $1, there's 20 nickels. So these nickels will cancel, and I'm doing 9 divided by 20, which gives you the 0.45. So kind of weird, but I think the point of these is practicing this unit conversion. So let's keep going with the example. For B, it says we have 2 quarters. And I want to convert this to cents. I want to convert the quarters unit into the cents unit. So you can imagine doing the same thing, converting like ounces to liters or something like that. So I put the unit I don't want on the bottom. I want to cancel the quarters and turn it into cents. And I know there is 25 cents in 1/4. So that can be my conversion. So 2 times 25 is 50. And that makes sense. We have 50 cents for 2/4. So for the second part, we want to convert this into dollars. So I have 2/4. I want to cancel the quarters, turn it into dollars. And I know there's 4/4 in $1. So 2 divided by 4 is 1/2 or 0.5. Yeah, 50 cents. And then part C, 9 nickels and 2/4. Well, we've already found out in cents and dollars for each one, so 45 cents plus 50 cents, that's 95. And 95 cents, well, that's 0.95. We can do that by adding these two together. Maybe I'll just do that for the sake of showing it. So we're doing 0.45 plus 0.50, so 0.95. So let's look at example 8. This time they want us to do it in a general form. Now they just say N nickels and Q quarters. So they're building us up to solve a certain kind of word problem here, I think. But let's do that same thing. We're starting with N nickels, and they want us to find out how much we have in cents and how much we have in dollars. So N nickels, let's keep doing that same process. I'm going to multiply this by something where I want to cancel the nickels and pick up cents. And we said earlier that there's 5 cents in 1 nickel. So the nickels will cancel and we'll get 5 times N. So if we have some number of nickels, N, we can multiply it by 5, and that gives us how many cents we should have. And then for dollars, we'll start again with N nickels. I want to cancel the nickels and pick up dollars. And there's 20 nickels in $1. So we're doing N divided by 20, or 1 divided by 20 is 0.05. So we can write this as 0.05 times N. This is 0.05 times the N. So in B, now we have Q quarters, some unknown amount in quarters. So let's turn that into cents. So we have quarters on the bottom because we want to cancel, and cents on top. And there are 25 cents in 1/4. So this is like, you can view this as over 1. Q and the quarters will cancel. So Q times 25, you can write that as 25Q, and we keep the cents unit. And then we have Q quarters. We want to convert to dollars, so quarters are on the bottom, dollars are on top. And there's 4 quarters and $1. So 1 divided by 4 is 0.25, so we can say 0.25 Q. And then in C, it wants us to add them together. We have N nickels and Q quarters. So let's just add these results together for our answer. So we would have 5N plus 25Q. And this would give us our value in cents. Or we could say 0.05N plus 0.25Q, number of quarters we have, and this would give us our value in dollars. So again, a little bit weird. Let's see an actual example, and it might make a little more sense why they're having us go through these two examples. But the main thing I think to get out of this is this process of converting units, of canceling units by multiplying by some conversion factor or by a ratio. Let's look at example 9. So it asks us to write an equation and solve. So it says at the end of the day, Anna counts the money in the cash register of the bakery where she works. There are twice as many dimes as there are nickels, so that seems important. And they are worth a total of $5.25. So some total amount. Something must add up to $5.25. So it's asking us how many dimes and nickels are in the cash register. So we have some unknowns. Unknown number of nickels, unknown number of dimes. So let's define a variable. I can say, I'll say I'll just say n be the number of nickels. And then it says there's twice as many dimes as there are nickels. So this can be a little bit tricky. But the number of dimes should be twice as much as the nickels. It seems kind of backwards to say that. Like it's tempting to say, oh, there's twice as many dimes as there are nickels, so 2 times d would equal n. But that would be actually the backward statement. That would be saying the number of nickels is twice as many dimes, the number of dimes times 2. So let's flip that around. And I just write that because I used to make that mistake a lot. So we can say d equals 2 times n. If d is the number of dimes, the number of dimes is twice as many as the nickels, or we can read it backwards. There's twice as many. It's still kind of tricky to think about, but the total number of dimes is twice as many as the nickels. There's twice as many dimes as there are nickels. So keep an eye out for that. That might, I can see some easy mistakes there. That's what the statement is saying. There are twice as many dimes as nickels. So I know that the total amount, they're worth a total of $5.25. So I can imagine adding something together and getting $5.29 or 25 cents. So if I know I have n nickels, how much value would that be? That's kind of like what we were doing earlier. If we had n nickels, to find out how many dollars that's worth, we multiplied by its value in dollars. Each value of a nickel is $0.05. So let's do that here. If we do 0.05 times n. That would give us the value of however many nickels we have. And then we have some number of dimes, and a dime is worth 10 cents, so, or we could say 0.10. So if I know how many nickels, this will give us the value, and how many dimes, this will give us the value. The combined value should be $5.25. But notice this is in two variables. We've only been solving equations in one variable. But luckily we had this statement here, that D equals 2n, because there's twice as many dimes as there were nickels. So let's replace that D with the 2n. Now we have an equation just in one variable that we can solve. So let's solve this like we've done previously. But let's get rid of these decimals. We probably don't want to have them around. There's 2 decimal places. That's the largest number we have. So that means if we multiply both sides by 100, we should clear out the decimals. Let's do that. 100 times the first side, and let's do 100 times the second side. So I'll just write it out here for just to show what we're doing. And then here's our 525, and we're saying these are equal. So the 100 will distribute, and when it does that, it's going to move the decimal places 2 places to the right. 0.05 times 100 will just be 5. So we get 5n. 0.10 times 100 is 10, times 2n equals, and then this will become 525. If you're okay working with the decimals, you're definitely free to do that. But the text likes to show this practice of, or this strategy of clearing out the decimals. That can make it easier, especially if you're in a situation maybe where you can't use a calculator or something like that. So let's continue solving. We have 5n. 10 times 2 is 20, so that'll become 20n. And this is equal to 525. And then 5n plus 20n is 25n. Then we're solving for n, so let's divide both sides by 25. So we can say n equals 525 divided by 25 is 21. N equals 21. Let's say you didn't have a calculator or something like that, and we wanted to do, don't be afraid to do some long division on the side. Doing 525 divided by 25 doesn't go into 5. 25 goes into 52 2 times, because I know 25 times 2 is 50. Subtract these out, you get 2 left over. Drop down the 5. 25 goes into 25 1 time. So you can always do a little long division on the side. So for these kind of questions, they're giving you some, maybe you're solving for some unknown number of things that have a certain cost, and you know what the total cost is. Try to set up a statement like this, where you have your different unknowns and their associated value. Because if I have I know I have 21 nickels, or some unknown value of nickels multiplied by the price per nickel, or the value per nickel, and that would give you the total cost. And this just made me realize we've only given half of our answer. It wanted how many dimes and how many nickels. So we gave how many nickels. We know that there's 21. So I'll even come back here and because we want to answer in context of the question. So there's 21 nickels, and how do we find the number of dimes? Well, we said earlier there's twice as many dimes as there are nickels, or D equals 2n. So if there's 21 nickels, then the number of dimes should be twice that amount, or 42. So let's just answer in full context. We can say we have 21 nickels and 42 dimes. So that would be my full answer. It's easy to stop once you have something equals something, but let's remember what the question was asking of us. Cool. And you can plug that in here and see if you get 525. You should get that as the result. Okay, in our last section, this is a problem involving distance and rates in time. So these can be a little bit tricky. It's helpful to write things out, but let's read through and see what they're giving us. So it says 2 planes leave St. Louis, one flying east and the other flying west. The westbound plane travels 100 miles per hour faster than the eastbound plane. And after 1.5 hours, they are 750 miles apart. And it wants us to find the speed of each plane. Well, one thing that we'll need to know is that speed. Think about like, how do we measure how fast our cars are going? Well, it's in miles per hour. It's distance over time. And we can very well multiply the time over to the left side and say that distance is equal to speed, or we can even say rate. You'll probably see the term rate a bit more frequently. Distance equals rate times time. You may have seen that as well. We'll need this, and we'll see why. So let's draw our situation. So we have St. Louis as some center point. And one plane is going west, and the other plane is going east. So we can call this the westbound plane, and this the eastbound plane. So one travels some distance, call that like d1, and the other travels some other distance, d2, over this 1.5 hour period of time. And we know the total distance, so this total distance between them after an 1.5 hours should be 750 miles. And we need to find the speed or the rate of each plane. So let's just call r the rate of the eastbound plane. And it says the westbound plane is traveling 100 miles per hour faster than this. So we can say r plus 100 is the westbound plane's rate. Make a little room. So we know that after 1.5 hours, so that's a time value. The distance traveled, distance of the westbound plane plus the distance of the eastbound plane adds up to 750. So we're writing out what our equation is going to be. And notice earlier I said distance is equal to rate times time. So this will allow us to plug in and basically like replace, we're coming up with this formula for distance. We'll be able to replace it with some values that we're coming up with. Sorry, I just had to move my tablet really quick. Okay, so let's replace distance of the westbound plane. This will be the rate of the westbound plane times the amount of time. And we know the time has been 1.5 hours. So that'll be helpful. So this will be the rate of the westbound plane. We said was r plus 100. And the time has been 1.5 hours. And then the distance of the eastbound plane, also rate times time. And we said the eastbound rate was just r, and the time is 1.5. So this should be equal to 750. I'll take out the hours here just so we're looking at all numbers, but we do have those units. So notice now we've finally arrived at an equation in one variable that we can solve for. So again, you might see variations of this problem in the homework. Try to find some total distance. We're trying to add up two distances to make a total distance. And if they're telling you the speeds of maybe like a car or something like that, bicycle, keep in mind this fact that distance equals rate times time. Or maybe you would need this form. So one of these two should be helpful. So let's solve this for r. If I wanted to clear these fractions, so let's practice doing this, say like without a calculator. I can multiply both sides by, in this case I would just want to multiply by 10 in order to move that decimal place over one spot. So let's multiply this by 10 as well. So when we do that, the 10 times 1.5 will turn that into 15. Then this will become 15r. And then this will become 7500. The 10 will add another 0, 7500. Okay, let's distribute the 15. You can do it from this side too. Usually we're used to seeing it on the front and distributing, but you can distribute from the other side as well. So this will become 15r. 15 times 100 will add 2 zeros, 1500. Then we have plus another 15r equals 7500. We have two like terms, the 15r and the 15r. So let's add those together. That'll give us 30r plus 1500 equals 7500. Now we can subtract the 1500 from both sides. So I will get 30r, and 7500 minus 1500, that should be 6000. And then I want to divide both sides by 30. Solve for r. Let me scoot down little more. So we're saying R is equal to 6,000 divided by 30. So let's do that division. Go off on the side. This should divide nicely, because I know 3 goes into 6, so these should divide. So 30 doesn't go into 6, but 30 goes into 60 2 times. Oops. Because 30 times 2 is 60. And then we have these 2 extra zeros. So that should add 2 zeros here. So 30 times 200 should give us 6,000. So that means that R is equal to 200. So 200 probably miles per hour, right? We were saying, yeah, miles per hour was our unit. So R, which one were we talking about? R was the rate of the eastbound plane. And then we're saying the westbound plane is going 100 miles per hour faster than that. So let's state our solution. So we can say the unit was the eastbound. So, and it was wanting the rates, right? The rate of each, find the speed of each plane. So we can say the eastbound plane has a speed of 200 miles per hour. And then the westbound plane goes 100 miles per hour faster than that. So this has a speed of 300 miles per hour. And that will be our solution. So I know it's a little bit kind of all over the place with this one, but just to go back through the general setup. You're probably given 2 objects that are traveling at 2 different speeds. And maybe you're given some total amount of distance between them after a given amount of time, or some variation of this. So it's helpful with these two ideas in mind, that rate is, or speed is, distance over time, or you could say distance is rate times time. It's helpful to draw out maybe a little diagram. I will usually start there. In this case we had a starting point and they went in 2 different directions. And they have some total amount. So I know the distance traveled by the westbound plane plus the distance traveled by the eastbound plane equals this total distance. And so that's what I wrote out here. So translated, just wrote out the word version. We had to define a variable, so we said R was the rate of the eastbound plane, and then the question said the westbound plane was 100 miles per hour more than that. And so here we are using the fact that distance is rate times time for each of these. So the rate of the westbound plane, which was R plus 100, times the amount of time that went by. And then similarly here, the distance of the eastbound plane is R, the rate times time. So we're just using that distance equals rate times time idea. So these 2 distances added up equals the total amount. And then from there, we just need to solve it like we're solving an equation. At that point, we can go back into solving equation mode. So the setup for these can be a little bit tricky. It's helpful to write out what they give you, what they're looking for. Try to draw maybe a little picture if that's helpful. Maybe write out in words what they're describing. And then you can try to convert the words into some kind of equation that we can solve. So there should be a couple of these style that you can practice on. All right, I think that finishes up this section. So this was 2.6, still solving equations, but this time we are using ratios and proportions. We had those money problems that were kind of about unit conversion, and then we finished off by solving that problem involving distance, rate, and time. So that'll be it for this video, and I'll see you next time.